So let us begin. Before I get into anything technical, what is this project actually doing? We are building a system that looks at a picture of someone's eye and automatically draws a precise outline around the white part. The white part is called the sclera, and the blood vessel patterns on it are unique to every human being, like a fingerprint, but for your eye. So if you can segment it precisely, you have the foundation for a contactless biometric identification system. The two status on the screen show our results. One model trained only on computer-generated fake eyes and one trained on a mix of fake and real eyes. Those numbers on the right, 0.95 and 0.93 F1, are better than anything that won last year's international competition on this exact task. Everything I explain is in service to achieving those numbers. So let's do a quick demo before we go any further. So we have the mixed model. Let's run it. As you can see, these are the segments with biometric pixel level precision. Let's try running the synthetic model now. And so is the result for the synthetic models. Let's go further. Technically, what we are asking the computer to do is look at every single pixel in an image and answer a yes or no question. Is this pixel part of the sclera or not? That's called binary semantic segmentation. The challenge list on the right is why this is hard in practice. Lighting changes, the eye looks different depending on gaze angle, eyelashes occlude parts of the sclera. And most importantly for this competition, our training data is mostly computer generated fake eyes. But the test data is real photographs. Those two worlds look quite different to a model. That gap is the central problem we are solving. To solve this, we built a pipeline that chains together several components. Two of these components, Dino V2 and Clip, are enormous pre-trained AI models developed by Meta and OpenAI respectively. Each trained on hundreds of millions of images. We are not training those from scratch, we are borrowing their knowledge and steering it toward our specific task. The parameter table makes this concrete. 84.9 million parameters are completely frozen. We never update them. We do all our learning with just 3.19 million parameters, which is 3.6% of the total. That's the architectural philosophy we have. This slide lists the 5 things we did that aren't standard practice. For now, think of it as just a checklist. As we go through the pipeline, each of these will come up and I'll explain why we made that specific choice instead of the obvious default. By the end, this slide will make complete sense. This is the bird eye of our view of our system before we go into detail. An image comes in on the left and a precise sclera mask comes out on the right. In between, there are 5 stages. The image gets broken into patches. Those patches get enriched with language understanding. They get reorganized at multiple spatial scales, then progressively decoded back to full resolution, and finally a binary decision is made at every pixel. The red stages S2 and S4 are where our novel contributions live. Everything else is principled assembly of known components. The first stage uses a model called Dino V2, which is a vision transformer, VIT for short. To understand what it does, imagine cutting the input image into a grid of 324 small 14 cross 14 pixel tiles called patches. Each patch becomes a vector of numbers, a linear vector of numbers, a compact description of what's in that tile. Then all 324 patches talk to each other through a mechanism called self-attention, so each patch can incorporate context from the entire image. What makes Dino V2 special is how it was trained, not with labels but by showing the same image in different ways and forcing the model to produce consistent descriptions. This produces patch representations where semantically similar regions naturally cluster together, which is exactly the property a segmentation system needs. Self-attention is the core operation inside each transformer block. The intuition is simple. Every patch computes a score against every other patch, asking, how relevant are you to understanding me? Those scores determine how much each patch borrows from the others. The critical difference from older CNNs is that this happens globally in a single step. A patch at an inner corner of the eye can directly attend to a patch at the outer corner in the very first layer for understanding the full context of the scleral region, which spans the entire visible white of the eye. The global view from layer 1 is enormously valuable. This diagram traces exactly what happens to the image data as it flows through Dino V2. The image enters, gets sliced into patches. Each patch becomes a 384 dimensional vector. Positional information is added so the model knows where each patch came from, and then 12 rounds of self-attention process the whole sequence. The important thing to note here is the shape stays 324 by 384 throughout all 12 blocks. The low rank adaptation, which I'll explain next, adds a small correction to each block's computation without changing any of those dimensions. We want to adapt Dino V2's behavior for our specific task, recognizing eye anatomy without destroying the general knowledge it accumulated throughout the pre-training on 142 million diverse images. The technique we use is called LoRa, low rank adaptation. Instead of modifying the original weight matrices, we add a small bypass path, two small matrices A and B that learns the task specific correction. The crucial design is that B starts at 0. So the bypass contributes nothing at the very beginning of training. The model starts as the perfect copy of Dino V2 and only deviates as evidence from our training data builds up. It's like learning to specialize without forgetting what you already know. The code on the left shows how clean the implementation is. LoRa linear wraps the original frozen layer. The original computation still runs. The LoRa bypass runs alongside it, and their outputs are summed. The freeze protocol on the right ensures that when we compute the gradients, only the LoRa parameters A and B receive updates. Everything else is locked. We inject 12 of these adapters, one into each transformer block, totaling just 590,000 trainable parameters, compared to 21 million if we fine-tune Dino V2 fully. This diagram makes the parallel paths visually explicit. The top paths is the frozen original weight. It always produces the same output for the same input no matter how long we train. The bottom path is the LoRa bypass, which starts contributing nothing and gradually learns the sclera specific correction. Their sum is what flows to the next stage. This guarantees the model can never do worse than the original Dino V2 at the start of training, which makes the optimization much more stable and reduces the risk of catastrophic forgetting. CLIP is a model from OpenAI that was trained on 400 million image text pairs, essentially learning to connect what things look like with what words describe them. We are using only its text half here. We give it 4 different ways of describing the sclera in plain English, things like white part of the human eye. All these four sentences are hard-coded, and it converts each description into a vector of numbers. We then average those 4 vectors to get a single stable semantic anchor representing the concept of sclera. The code block on the right shows this process: encode, normalize, average, cache. Here's the problem this solves. Dino V2's patch tokens describe what's visually in each patch, but they have no concept of what a sclera is. They might describe texture and color accurately, but they don't know what the white region that they're describing is semantically meaningful as a biometric structure. CLIP does know, so we inject that knowledge, the semantic anchor from the text encoder, directly into the patch token sequence. Before any spatial decoding happens, every downstream computation then operates on features that are already biased towards sclera relevant information. And since we compute the text embedding once and cache it, this adds 0 cost per image. The mechanism that fuses the text knowledge into the patch tokens is called cross-attention. Think of it as a question and answer process. Each patch token asks, how similar am I to the concept of sclera? The text embedding by CLIP answers. The answer gets added back to each patch token as a correction. Patches that look sclera-like get pulled towards the semantic anchor. Patches that don't are relatively unaffected. This diagram shows the asymmetry clearly. Patches are the queries, the text embedding is the key and value. The residual connection as the output ensures we are adding to the Dino V2 representation, not overwriting it. After the patch tokens have been enriched with language grounding, we need to convert them into spatial feature maps that a CNN decoder can work with. The problem is that Dino V2 only produces a single resolution and 18 by 18 grid of tokens. For precise boundary segmentation at 256 cross 256 pixels, we need features at multiple scales, coarse features for understanding what region is sclera, and fine features for knowing exactly where the boundary is. The feature pyramid network solves this by taking that single 18 cross 18 representation and producing versions of it at 3 different spatial scales using cheap bilinear sampling and a small projection convolution at each level. This diagram shows the 3 scales emerging from the same source. 64 cross 64 pixels with 96 channels for fine spatial detail, 32 cross 32 with 192 channels for mid-level context, and 16 cross 16 with 384 channels for high-level semantics. These 3 feature maps are what the decoder receives as its inputs, one at each upsampling stage. The decoder's job is to take those small feature maps and progressively reconstruct the full 256 cross 256 resolution. At each upsampling stage, we use a dense block, which is a specific way of arranging CNN layers, where each layer receives the outputs of all previous layers as additional inputs, not just the one immediately before it. The practical benefit for us is that fine-grained boundary information captured early in the block is never discarded. It stays directly accessible to every subsequent layer. For sclera segmentation, where the boundary between the sclera and iris can be just 1 or 2 pixels wide, this persistent access to early features is what lets us localize boundaries precisely. After each dense block, we apply an attention mechanism called CSSE, concurrent channel and spatial squeeze excitation. Think of it as 2 independent spotlights. The channel spotlights, CSE, looks across all the features and decides which ones matter most right now. The spatial spotlight, SSE, looks across all locations in the image and decides which regions deserves more focus. They answer orthogonal questions: which features and where. The math on each side of the slide shows they operate on completely different dimensions. The word concurrent is the important design choice here. We run both spotlight mechanisms in parallel and sum their outputs. The alternative, running one after the other, would mean the second mechanism operates on already modified features, creating a dependency between them. Running them simultaneously keeps them independent so that we can specialize in their own distinct roles without interfering with each other's gradient signals during training. This diagram makes the parallel structure immediately clear. Input goes into 2 branches simultaneously. Each branch produces a recalibrated version of the feature map, and those 2 outputs are summed. No information flows from one branch into the other, and they are genuinely independent until they meet at the addition. This diagram shows the full decoding process across all 3 stages. Starting from the coarsest 16 cross 16 features, we upsample, concatenate the corresponding FPN features, refine with dense block plus CSSE, and repeat. After 3 rounds, we have a 128 cross 128 feature map that has been progressively refined at every scale. The output head then takes it to the 256 cross 256 and produces the final mask. The output head is intentionally simple: a 2 times upsampling to reach 256 cross 256, a 3 cross 3 convolution to aggregate local context, a 1 cross 1 convolution that collapses to a single channel, 1 number per pixel representing how likely that pixel is sclera. We then apply a sigmoid to convert that to a probability between 0 and 1, and threshold at 0.5 to get the final binary mask. This slide is the engineering receipt. Every tensor shaped at every stage of the pipeline in one place. For anyone familiar with PyTorch, you can read off exactly what's happening dimensionally. For everyone else, the key takeaway is that the image starts at 256 cross 3 and the mask comes out as 256 cross 256 cross 1. And all the interesting information transformations happen in between. Now this is the complete system in one diagram. You can see the frozen components on the top, dyno V2 and clip, feeding into the trainable components below. The thin connections between the frozen and trainable are where the adaptation happens. Low rank adaptation inside dyno V2, cross attention receiving the clip embedding. Everything else downstream is learned from scratch on our training data. To train the model, we need a loss function, a way of measuring how wrong the current prediction is, so we can improve it. We use a combination of two losses. The first, binary cross entropy, penalizes each pixel individually, independently. If a sclera pixel is predicted as background, that's an error. But PCE has a known failure mode. When the sclera is only 20% of the image, a model that predicts everything as background gets 80% of the pixels right, which BCE doesn't penalize strongly enough. The second loss, dice, directly measures the overlap between predicted and actual sclera region. It's immune to that class imbalance problem. We weight dice at 60% of the loss and BCE at 40% to make the region overlap the primary objective. We train using AdamW optimizer with one important wrinkle. The LoRa adapters use a learning rate 10 times smaller than everything else. The reason is that LoRa is modifying the behavior of a frozen pre-trained backbone. If you push too hard, even do the representations, dyno V2 spends enormous amount acquiring. Gentle adaptation is the right strategy here. The learning rate follows a cosine schedule, cosine annealing, starting at 1e minus 4, smoothly decaying to 1e minus 6 over 70 epochs. The log line at the bottom right confirms the schedule to happen exactly as expected. During training, we artificially vary the input images before feeding them to the model. This forces the model to learn features that are robust to lighting changes, rotations, blurriness, and compression. All the things that vary between a controlled synthetic image and a real photograph taken in a while. The most domain-specific augmentation is the specular highlight simulation in the bottom table. We add bright Gaussian blobs to training images that mimic the corneal reflections you see in real eye photos. These reflections are visually almost identical to scleral light, making them the primary source of false positives. By exposing the model to them during training without labeling them as sclera, we teach it to ignore them. Our training data comes from three sources. Synchroi is a dataset of 11,000 computer-generated synthetic eye images, clean, well annotated but not real. MASD and SBBBI are real photographs taken in actual conditions with a total of 4,400 images between them. The bar chart makes the scale disparity obvious. Synthetic data dominates numerically. The cache statistics at the bottom are from the actual training log. We preload all 4 gigabytes of the data into RAM before the training starts, which is why training batch only takes about a quarter of a second. This slide is a core strategy decision. The synthetic only model, despite achieving 0.977 F1 on synthetic validation data, drops to 0.8795 when tested on real photographs. That gap's nearly 10 percentage points is the synthetic to real domain gap. The mixed strategy incorporates real images during training at 3 times oversampling. The oversampling is necessary because without it, real images would be numerically overwhelmed by the 10,000 synthetic samples and the model would barely learn from them. The result of mixing, test F1 on MASD jumps by 7.5 points, SBBBI by 6.7 points, while in-domain validation drops by less than half a point. The learning curve here shows a healthy training run. It rises steeply in the first few epochs. The frozen innovative features are already highly informative from day one. So the trainable components converge quickly. Then it flattens into a long gradual improvement as the cosine learning rate schedule anneals. The synthetic model's curve is cleaner simply because it's training on a single consistent data distribution. Each epoch takes 78 seconds instead of 171 because there are fewer batches. The model improves monotonically all the way to epoch 70, which tells you it hasn't saturated the 10,000 synthetic training samples even after 70 passes through the data. The best validation F1 of 0.977 represents essentially the ceiling of in-domain synthetic performance. These tables let you read the convergence story precisely. Both models do most of their learning in the first 20 epochs. Look at the jump from epoch 1 to epoch 20 compared to epoch 20 to epoch 70. The last 50 epochs are refinement, squeezing out the final percentage points as the learning rate falls. The bar chart at the bottom summarizes the key comparison. Mixed training is dramatically better on real-world data. These are the numbers that matter for the competition, held out test sets that models never saw during training. The metric bars make the improvement from synthetic to mixed training visually immediate. The scatter chart on the right shows something reassuring. The mixed model's performance on real data is close to its own validation performance, meaning it didn't just memorize the real training images, it genuinely generalized. This slide quantifies exactly how much the domain gap shrank. Starting from a 9.17 percentage point gap between the in-domain validation and real-world MASD test performance on the synthetic model, mixed training brings that down to 1.83 percentage points. That's an 80% reduction in the gap. The remaining gap discussion is at the bottom. It's honest about what's left. A per dataset threshold instead of a fixed 0.5 we used across the board would likely close most of it. That's a known next step. Every number in the table comes directly from the training run log, not from a paper or default config. This is the complete specification to reproduce our results deterministically. Batch size, learning rates, schedule parameters, sclera rank, dense block configuration, loss weights, everything. The random seed is fixed at 42, so the experiment is fully deterministic. The inference code on the left shows the full prediction pipeline. About 20 lines of Python, load the image, resize to 256 plus 256, normalize using ImageNet statistics, run the forward pass, apply sigmoid and threshold, upsample to the competition's 400 plus 300 output resolution, save. We submit two independent checkpoints, one for the synthetic only model and one for the mixed model, as per the SSPC 2026 track 1 requirements. The inference runs at approximately 4 milliseconds per image. That's fast enough for a real biometric system operating at 30 frames per second. The final slide is a technical FAQ. Each accordion covers a question that goes deeper in the main presentation. Things like why is B initialized to 0 in LoRa, or the algebraic relationship between dice and intersection of union. I'll leave this open for questions from the panel.